So this lesson is all about how we evaluate limits algebraically. You're going to notice that I have some graphs here, and they are just for reference for the functions that we use. But the goal of this lesson is to show us how to evaluate a limit when we don't have a graph. Okay. So the first thing that we can do with our limits is actually plug in whatever our value of a is. So this function is x squared minus 4, and I have this over here to the right. And you'll notice that if we were to look at this graphically, the limit from the right and the limit from the left both approach -4. And because this is continuous, this function is continuous, we can actually just plug in our value of 0. So this becomes 0 squared minus 4, or 0 minus 4, -4. So the disclaimer, though, and I'll use a different color here, our disclaimer is that it's only this easy if our function is continuous. Because the function is continuous. And specifically, it's continuous at that value x equals a. So in this case, a was 0. Since the function is continuous at 0, we can just plug that in. So if we keep going and we say, okay, well, 2x plus 4, that's just a line. That function is continuous. That means I can just plug in 3 for x, and I have 6 plus 4 is 10. Okay, so go ahead and pause our video here for a second so you can try the other 3 as an example. All right, now that you've paused and unpaused and given those a shot, we'll look at our examples here. So the limit as x approaches -2 over there. So this is a continuous function, so I can just plug in -2, and we have 3, -2 plus 1. -2 plus 1 is -1, so we get -3 as our limit. Okay. 3x minus 2 cubed, that's a continuous function, so I can substitute 1 in for x, and we have 3 times 1 is 3, minus 2 cubed equals 1 cubed equals 1. So far, piece of cake. And then last, if a is 8, cube root of x is a continuous function at 8, so I can plug that in there, and I have 1/4 times 2, or 1/2. So everything's nice because our functions are continuous and we can plug in those values of a. So what happens if we have a function that is discontinuous at x equals a? So this function that we're looking at here is x minus 2 over x squared minus 4. Now if you recognize, there is a hole in this graph, and we also have the hole here in the graph to the right. So this is the graph of x minus 2, x squared minus 4. So if we didn't have the graph and we didn't know that this function was discontinuous, what would happen? So we notice that if we plug in 2, 4x sorry, that's should be squared. We end up with this indeterminate form, 0 over 0. All right, we're going to call this an indeterminate Now, the notation that I'm using here, unfortunately, this isn't super correct to put the equal sign there, but I'm just going to do that for now. And then later, when we get back face to face, we'll talk about some notation when we're answering questions like this. So we get something that's in an indeterminate form, and so I can't just leave it and say like, oh, okay, it's 0, it doesn't exist. Because if we remember that this limit exists, this limit is something, right? Because the general limit exists because the left-hand limit from the left here and the right-hand limit are both approaching the same thing. It's discontinuous because that point isn't defined. So what we can do is actually simplify, just like we would if we were looking for the hole in that, that removable discontinuity. And we can actually say that x minus 2, that x squared minus 4 becomes x plus 2, x minus 2. We have x minus 2 and x minus 2, which cancels out. And that gives us 1 over x plus 2. So now I'm evaluating the limit as x approaches 2 of 1 over x plus 2. And you may think, well, Mr. Schreiber, that is also a discontinuous function. Yes, this function is discontinuous, but it's discontinuous when this is discontinuous when x equals negative 2. And you can actually see that here on the graph. We have our vertical asymptote here where it's discontinuous. So because it's discontinuous at negative 2, but it's technically continuous, this function is continuous at positive 2, we can go ahead and plug in negative 2 here, or positive 2. And we can say this is equal to 1 over 2 plus 2, which is equal to 1/4. So the value of that limit is 1/4. Okay. So we have a couple other examples here that will end up being functions that are discontinuous. So for example, I'm going to zoom in here, and I'm going to make my pencil smaller. So if I were to plug in 1 to, and if I were to plug in 1 for x in this function, we would have 3 minus 3 over 1 minus 1, and that is 0 over 0. But we can't just say that the limit is 0 over 0. All right, we have to actually evaluate it. And we can actually start by factoring out 3. And I can factor some more. I notice now that these two are common factors, so I can cancel them out. And I'm left with 3x plus 1. And so now I'm evaluating this limit, my limit, as x approaches 1 of 3x plus 1. And I can simply plug in 1 for x here. And looks like it's going to be 6. When I evaluate that, 6. Okay. And I'm going to move this problem over a little bit so we get some more room. And then same thing here. So we notice that if we plug in 2, we have 8, 2 cubed minus 64, 2 minus 2, 8 times 8 minus 64. You probably see where this is going. So we end up with 0 over 0. So that's an indeterminate form. So we can simplify and factor to solve. So in my numerator, I have 8x cubed minus 8 over x minus 2. And we're actually going to use the difference of two squares for our factor. So difference of squares says we do, or sorry, not difference of squares, difference of cubes. And difference of cubes says let me double check to make sure. I always have to look up difference of cubes to make sure I'm doing it right. So difference of cubes says we are going to take x minus 2, and we are left with x squared plus 2x plus 4 all over x minus 2. Here are my common factors, and I'm left with 8 times x squared plus 2x plus 4. So now that I've simplified, that's the limit that I'm taking. The limit as x approaches 2 of 8 x squared plus 2x plus 4. And I can find that just by plugging everything in. So I'm going to kind of do some mental math here. Let's see. So 2 squared is 4. Two times 2 is 4. And this gets me 12 times 8. So 12 times 8 is 96, I believe. Yeah. So our limit is x approaches 2. And I'm going to kind of write this off to the side here. So as our original, this limit, 8x cubed minus 64 x minus 2, that limit equals 96. Okay. Alright. Okay, that's a little bit of work there, but that's alright. So what we're going to do if we have piecewise functions, okay, or not piecewise functions, but discontinuous functions. Got ahead of myself. But now what happens if we have a limit of a piecewise function? So if I'm given this function f of x, right, how do I know that this limit exists? And the limit that we're going to look at is where the rule changes, and the rule changes at -3. So how do I know that this limit exists at -3? So I've graphed it just to help us visualize, and we see that, okay, this limit doesn't exist because the left and the right hand limits aren't the same. So how do we prove that? So we can prove that by setting them equal to each other. 2x plus 2 equals x squared minus 4. And we're setting them equal to each other because if those two pieces are equal to each other, then we know that the limit will exist. So for like example, if this line here were scooted up so that it was instead here, we would say, oh yeah, it's continuous, even though they're two different pieces. So now I'm going to go ahead and plug in -3. And simplify, so -6 plus 2 equals 9 minus 4. We have -4 equals 5. So those two things are not equal. So we would say that the limit as x approaches -3 of f of x does not exist. DNE. Alright. So let's do the same thing for this function here, f of x. And so, like I said, if we want to see if the limit exists, we want to see if the left-hand side and the right-hand side are the same. So I can start by setting them equal to each other. And I can substitute 1 in for x and say that 2 minus 3 is -1, 3 minus 1 is 2. These are not the same, therefore this limit does not exist. If they are the same, then whatever that number would be is our limit. Okay? So we've looked at a few limits. We have some discontinuous limits. We have some continuous limits. And now we want to talk about how we can use limits to determine what type of continuity or discontinuity a function has. So this should really say using limits to define continuity and discontinuity. Okay. So there's 3 requirements for a function to be continuous. The first requirement is that our general limit has to exist. Notice the symbol here, there's no plus or minus, so the general limit has to exist. All right. The next requirement is that f of a, and a being this value here, whatever f of a is, it has to be defined, okay? It has to be a number, all right? And then our third requirement is that our general limit and f of a are equal to each other. So let's look at a couple examples here and talk about what requirement is broken that causes it to be discontinuous. These are 3 functions that are discontinuous. Why are they discontinuous? Which one of our rules is being broken? So the first one here, if we are looking at -3, we see that it's discontinuous, and it's discontinuous because the first rule, that general limit, does not exist. So let's say, we can say this is discontinuous because the limit as x approaches -3 of f of x does not exist. Our second example, so we see a point of discontinuity, but now we want to figure out, okay, what rule is being broken? So number 1, does the limit exist? Yes, the limit exists here. This and this are approaching the same thing. But how about number 2, is f of a defined? No, f of a is not defined. So we would say discontinuous because f of 2 is undefined. all right? In our last example, okay? Does the limit exist at 3? Yep, limit exists. Everything's approaching the same value. How about f of a is defined? Actually, yep, f of a is defined. It actually equals 2. But notice that our last rule is being broken, that the limit is not equal to f of a. So we can say that this is discontinuous. Because the limit as x approaches a of f of x does not equal f of a. Alright, so those are some examples and some explanations that will help you with your problem set today. Give those a shot. You can always refer back to the videos as you are working.